Hey, it's Mathman Dan. We love going around finding out where math shows up out in the real world, and we especially love talking to people who use it in their jobs. And today, we are at Northrop Grumman in the Rancho Bernardo area of San Diego, California, with Bob. And Bob, we've been talking, you actually know a lot of math, even though I guess in your job title you don't directly use math every day. But how did you arrive here at Northrop Grumman?
Well, you're right, I don't. I was an engineer by academic degree, but I spent 29 years in the Navy as a carrier fighter pilot, and then I joined Northrop Grumman as a business development manager.
So you actually took a lot of math in college, I take it?
I did, right.
And it was fun, right?
I took all the stuff you're teaching right now, calculus, differential equations, and then took those tools and applied them to aeronautical engineering.
Sounds good to me, of course. So one of the things I was talking to you about was all the different kinds of engineers here, and in fact, you guys need engineers right now.
Oh yeah. In fact, I don't think you'll find any major defense company that isn't really hungry for engineers today nationwide. We have open recs for several hundred just in Northrop Grumman alone.
So despite the economic times right now, you guys are actually actively hiring
Absolutely.
engineers right now.
We are actively hiring engineers. If you go to our website, you'll drop the career menu down, and you'll see dozens and dozens and dozens of engineering jobs available.
So I'm trying to tempt people that math can be a little fun and exciting. So we've walked around here a little bit, so I know. But tell people what you guys are making here.
Well,
it's pretty impressive.
We're in Rancho Bernardo, and we primarily do all the unmanned air systems or air vehicles for Northrop Grumman, and we manufacture a handful up in Palmdale and in other places around the country. And our engineering and program management staff is primarily here in Rancho Bernardo. The products that we support here are the Global Hawk, and there are several different blocks or variants of that vehicle. The Global Hawk is
It's an unmanned vehicle?
These are all unmanned vehicles, and the Global Hawk is a large, high-altitude, long-endurance sensor platform. And
okay. Is that something we would have seen on the news?
Oh, absolutely, yeah. They're operating in combat theaters today.
Okay.
And their real value is we can put them up and leave them up for a long period of time, and they transmit the information that they see, and they have sensors across a wide electromagnetic spectrum, whether that be radar imagery or infrared imagery or electro-optic visual spectrum. They do all of this, and then they transmit that to our to the military analysts.
So your engineers here, if someone got a job here, some of them would be doing the physical engineering, if you will, actually
Absolutely.
Designing the crafts.
Right. In fact, if you looked at the spectrum of engineering talents, they run the gamut from electrical engineers to aerospace engineers, mechanical engineers. We even have some, chemical engineers. We do propulsion analysis and.
Oh yeah, I wouldn't have thought of chemical, but yeah, sure.
Absolutely.
And I assume software.
Oh yeah. Software and computer science are big pieces of what we do, especially in the unmanned world, because we're really on the cutting edge of developing new sciences and new techniques for making these aircraft do their missions without actually having a man in the cockpit.
So no pilot in there means lots of electronics, I take
well,
it.
In today's world, any sophisticated airborne or platform with military utility is going to have avionics in deep supply.
Sure.
Absolutely. Communications gear, navigation.
So communications, is that GPS and satellites?
We use all of those methods, inertial navigation systems, GPS as you mentioned. We use satellites not so much other than for GPS navigation, but we use them for communications.
Okay.
Right.
So all the various engineers obviously all have to use a lot of math in their job day to day, I would guess.
Well, absolutely. A strong math background is just a fundamental piece of any engineering discipline.
But you know what I noticed, because we've talked to several engineers here today, they all are very excited about their job. They all look like they're having a great time,
Yep.
and they enjoy the math, and they get to play with some amazing toys. I mean, you guys are working on a new craft right now that is just amazing.
That's right. These guys are actually inventing stuff. That's absolutely right.
So they're having a great time. So hey, look what math can do for you. It can be really fun, actually. Bob, I want to thank you for showing us around today. I learned a lot, actually.
Good.
And I'm hoping we inspire some people to consider putting a little more math in their career choices, perhaps, because it really is a good way to go.
You bet.
So hopefully we'll see you again sometime.
My pleasure, Dan. Thanks for
Bob.
coming out.
We actually got to talk to several really cool people at Northrop Grumman, but Bob was especially informative, so we want to thank him for talking with us that day and giving us a little overview of what was going on there. I was actually quite impressed, but I mentioned we got to talk to several people. We got to talk to one of the engineers, actually, and we're going to show that to you a little later in the program. He went into some specifics of the things he plays with all the time. But if you want to go check out some really cool toys that they're playing with, they have a lot of information on their website. And as he mentioned, they're looking for talented people. So get a little math under your belt. Look what you could be doing. Hey, it's Mathman Dan. We are out in the field, as they say, looking at where mathematics shows up. We love talking to people who use math in their job. And today we're at Northrop Grumman in the location Rancho Bernardo, California. This is Abel. And there's lots of engineers here. We wrangled one of them up. You are an engineer, right?
I am an engineer. I'm flight test engineer for the X-47B unmanned air vehicle.
Okay, so there's lots of cool stuff going on here, but first, how did you get here? Have you always been a math fan?
I've always been a math fan. My dad's engineer, so I got into it. I graduated from Texas A&M. I have a degree in engineering technologies, emphasis in control laws. I have a minor in business, a minor in math, and a minor in computer science. 7.5 years in school.
Very impressive pedigree. So basically here, they're making only unmanned aircraft, right?
Correct.
No
Here
pilots.
in Rancho Bernardo, we emphasize on unmanned aircraft only. The target aircraft, of course, has been around since 1958. We've sold a couple 100,000 of those. And then we have other aircraft that have been developed since then, and now we're on the cutting edge. The X-47B is the next generation.
This is the new one you're working on.
This is the new one.
Okay, so I've seen a little bit about it. It's very, very impressive. And obviously there must be tons of math and engineering that goes into it. But you actually told me quite a bit. But one of the things you're talking about is this whole idea of all the systems on there that have to sense for things, and kind of like the autopilot systems, if you will.
We call they're called control laws. And the simplest form of a control law is a proportional integral derivative controller. And I know.
Wait, integrals and derivatives right there.
Yes.
Those are the calculus ideas, right?
All calculus. And we take calculus kind of to the next step, and we go into differential and discrete mathematics. But the concepts are fairly simple. You take an airplane, and you tell airplane, I want you to go from point A to point B, and you give it a path that it's going to go follow.
Is this in the air? Or?
Well, we'll just talk the runway.
Okay, just
simple.
All right, sure.
And so
Around the runway.
we have this cool thing, it's called a navigator, and it knows where it's at on the face of the planet. It says, here's where you are at. And the guidance, navigation, and control laws say, okay, navigator, this is where I'm at. I want to go over here. So it says, turn the nose wheel steering this way. So the nose wheel steer turns, and the navigator said, hey, you moved. And then that feeds back in, and the guidance, navigation, control says, oh, we moved, okay. So they change their command a little bit, and the navigator says, oh, you moved again. And they close that loop. And what happens is you have a command that goes out to a plant, in this case, the airplane,
Okay.
that then feeds back through the navigator, and then we have a correction that's made, and then we send a new command out. And then that's called a closed loop control system, and that's what allows us to control an airplane to make it safe.
So I think most people would think autopilot they wouldn't realize that was what's going on. They would think like, oh, it just says steer here. But really what's going on is, it's not like there's some equations working off of as a path. It's like, it's continually looking where it is and then making little corrections. It's like feeding it over and over, right?
So the equations actually get broken down into matrix, and then you do matrix type mathematics to actually do that calculation. Then those equations change depending on what scenario you're put into. So if suddenly you say, I need to make a sharp right-hand turn to avoid, say, a tree or a deer or something in the road, the airplane makes a sharp right-hand turn, and those equations vary to make sure that they can handle that and they can do that safely. And so, yes, we do.
So constantly sensing what happened and then having some, I don't know, computer device, something, make a decision.
That's exactly what happens.
Make a correction and then keep doing this. How fast is this going on? Like several times a second or something?
This happens at least 100 times a second.
Oh, really?
Very, very fast. Some of the more tighter control systems
Wow.
may even go to 2 or 1,000 times a second.
So lots of math going on in this whole loop.
Absolutely.
Tons of times a second.
You have, when you talk about math, you have all the mathematics goes on. So there's the closed loop control that's just going around the actual driving of the airplane. Then you have things like the fuel systems. In our fuel systems, you take something that's very simple, like say, you normally look at a gas tank and you think of a rectangle and say, oh, it's got gas in it, and you calculate the volume. Well, Yeah, that's okay. Not really.
They're not rectangular, let me guess.
No, I mean these things sit up under the wing, and they have arcs on them, and so you have to do integral mathematics. You have to take integrals of functions to actually calculate the volume.
Just like our calculus students are learning, right?
Absolutely. Then you have these cool probes that sit in there, but there's no flat place. You can't just put the probe across the center of the thing and say, oh, well, when it's this full, it's going to be this much. No, you have 3 or 4 probes in there that are actually calculating how much fuel is in there. And you know, you have pumps that are pumping the fuel, moving it around to keep the center of gravity of the airplane at the right spot.
Oh, yeah. And people might be wondering, why would you have a weird shape? But it has to do with the balance of the plane?
Well, actually, the weird shape is because there's no square spot in the airplane. It's crammed in there pretty tight. So what happens is you have it up on the wings and up on the belly of the airplane is where the fuel tank's set. And so you're not going to go make the airplane square. The airplane's got to be very smooth so it moves through the air quick, nicely. So you have these odd shapes. So then you start talking about running the airplane through the air. Well, when you take off, that's going to make the fuel slosh. Well, you use common filters and other types of filters to get that data to smooth it out so that way you can kind of figure out exactly how much fuel is in that tank. Then you say, oh, well, I want to get a mass here. That's not a good place. Let's move the mass forward. So you turn on pumps, and then you start getting dynamics of the pumps, and you get...
So it's actually moving fuel around during flight.
We're constantly moving fuel on this particular airplane from the back to the front.
Wow. And it's the same idea of the control system where it's constantly measuring things and making adjustments.
Well, so you talk about suddenly we're no longer moving across the on that line. We're now in the air.
Yeah.
Well, in the air, if it's too heavy in the back, the nose is going to want to lift. So as you begin to move that fuel forward, it makes the airplane want to fly flat. Well, if you put too much fuel forward, well, now the airplane's going to want to dip. So now you have to correct that, and so you have a loop. You have a control law that says we're going to move the fuel like this, and we're going to keep the airplane stable in the air.
Wow. So how many of these control systems do you think are involved in that? Do you have any idea? I mean,
Thousands.
Really?
We probably close. Well, we'll go with hundreds. I'll go with hundreds. You have
At least hundreds,
we
okay.
have air data systems. We have closed loop controls on where we run the hydraulics. We have closed loop controls on how our gear is being managed. We have closed loop controls on pick an axis, pick a function, and we have closed loop control that says we've issued this command, we get this response. Some of them are very slow. Some of them only run it 1 or 2 times every 10 seconds. But some of them are very fast. That all kind of issues on how fast you need the response to be.
All of them doing mathematical calculations while they do this.
Yes, and some of the simplest forms and some of the most complex forms.
Now, in the other room you showed me, you have kind of like a disassembled craft in there.
Yes.
You actually, I saw some of these sensors, I mean the boxes, you know, and you actually sort of have it set up in there. I mean, it's all disassembled, but it's kind of like what the plane would be doing, right?
So technically we have everything in there that's safe. So we don't have fuel and we don't have rotating parts. So everything else is in there. And you're absolutely correct. What we do is say we take about a navigator or a brake control system. We convince the navigator that it's flying. So I can take that navigator and with some really cool sophisticated simulation, I can put it in China. I can put it over Antarctica. I can put it across the poles. And we get to fly the airplane wherever we want. And we get to go and test all the dynamics of the airplane and all the decisions that it makes.
It's crazy. In a good way.
Yeah, I enjoy my life.
So, Abel, how fun is your job?
My job is an absolute blast. There is nowhere else in the world that you can go take a 40,000-pound airplane, fly it through 3-dimensional space at a billion-dollar aircraft carrier, and go catch the third wire within 10 centimeters.
And it's going to do that.
Absolutely. I mean, this airplane, there's no tail, so there's no vertical stabilizer like you see on your 747s running around.
Yeah.
It's LO, so it's very smooth and it's got a very, very cool flight dynamics. And it flies itself, and it's, I mean, short of a hurricane, I mean, actually, probably in a hurricane, this thing will go and catch the third wire every single time on an aircraft carrier.
Wow.
Please tell me you have a cooler job than that.
Okay, so besides getting to play with some of the coolest toys on the planet, you guys are completely on the cutting edge of all this technology.
Short of actually defining the cutting edge, we are on it.
So I'm trying to inspire people that math can actually be a really fun way to make a living.
Well, in the classroom, you're given the tools. And so it gets a little rough. I've been there 7 years. I understand. It's rough. You're sitting there looking at this like, this doesn't make sense, and it's stupid. But
Hey,
suddenly you come out and you take that tool and you go and make something work like this system or, you know, autonomous car or a refrigerator. I mean, it doesn't really matter. Suddenly you apply it and you understand why it was so important. And that is just frippin' cool. You can't convince me.
all right, Abel, you've been very helpful for us, and we appreciate your enthusiasm because I'm hoping you inspire some people out there because you guys need more engineers here, right?
Absolutely. You can always find a job at Northrop.
Perfect. Abel, thank you so much. I actually learned a lot myself. So.
Thank you. My pleasure.
And if I can, back in the studio, maybe I'll show you some of these crazy equations he's talking about.
I will see if I can't get you a good book.
All right, awesome. Thanks. We'll see you back in the studio. All right, we really have to thank Abel for talking to us because he was very informative. He actually showed us lots of cool stuff. And he's very excited about it all. And I was going to try and follow up with a little bit of what he was talking about. Now, he's the expert and I'm the student here. So I learned a lot from him. But I did some homework on my own. I was going to try and show you one example of the kinds of things he was talking about. He was talking about these control laws they use to basically, it's kind of like how they run all the autopilot features of these aircraft. So he mentioned one in particular called a PID controller, and that was proportional integral derivative. And that one, of course, you know, I had all those calculus terms in it, so right away I was interested in it. But there are lots of fancy versions of this. There's whole textbooks on it, and you know, he specialized in this when he was in school. So it's a very big topic. But I was going to show you one simple idea, just so you get the idea of how these sensors actually work and how they actually can steer things. And well, one example I was going to use was like cruise control in your car. You could maybe even think of it as sort of the cruise control for the aircraft if you want them to go a certain speed. Now, if you think about it, if you're driving your car, you as a human, you're like the cruise control, because if you need to go faster, you push the gas and then you let up when you need to and you try and get to the speed you want. But how does a machine do that? It can't just look at your speedometer and instantly know, okay, I need to get you to 70 miles an hour. So this is an application of something like a controller he's talking about. And the idea is it would go in a loop, it would continually measure the speed you're at, the speed you want to be the goal, and they would try and make corrections to get you to the right place. But it's supposed to do it in a way that's nice and smooth so you don't get jerked around in your car, and also they want to do it fairly quickly. You don't want to wait forever to get up to the right speed, right? So what they look at, I've drawn a few graphs here on my computer I'll show you. We want to look at what's called the error, and this is simply the difference between the goal and the place you're at now. So let's say your goal is to be 70 miles an hour on the freeway with your cruise control, and right now you're at 60, you'd have a 10 mile per hour gap. That would be your error. And if you look at my graphs, I've drawn graphs that shrink because hopefully your error is getting smaller, right? You're supposed to be getting closer and closer to your target. So the error should be getting smaller and smaller as we go. So one thing you can do is simply measure the amount of the error itself, and this is the p part of that. So on my graph, I'm going to draw you a little line here. The height of this graph would simply be your error. So the p part is we can take a proportion of that. So let's say the error is 10 miles an hour. You could say, all right, I'm going to multiply that by 0.2, and that's the number of centimeters, or I'm going to push the gas pedal down or something like that. So you can actually use the amount you are away from the goal and have a little equation set up to tell you, just take a multiple of that, and that's how far we're going to push the gas pedal or let up on the gas pedal where it needs to be done. Well, that alone is going to get you towards the goal, but it's actually not a perfect solution. So the PID control has two other components to it. The next one, the I part, is for integral. Now, if you're in calculus class, you know what an integral is, but if not, it's okay, because really what you need to think about it for the moment is its area underneath a curve. So you would pick a spot here, how much time has elapsed, and you would find all the area underneath there. And what that does is it's kind of like an accumulation or a sum of all the errors so far. And the reason that can be used is because, let's say you start going uphill, and you've got to push the gas a lot harder, to get up that hill than what would happen on level ground. So the machine is trying to increase your speed, but it's just not doing it fast enough. So this accumulates all that error and says, hey, when your error starts piling up, meaning you're not doing good enough, I'm going to use this component to kick in some more, and I'm going to push that gas pedal down harder. Well, the last part, D, is for derivative. So by the way, I'll write you down some symbols because we're going to put this all together in a final equation here. So the first one, the P, that's just taking a multiple of the error itself. The next one, integral, you're actually going to integrate the area under the curve. So that's going to be how much time has elapsed. And by the way, if you're in a calculus class, you might have noticed I changed the variable x in there just to not get it confused with the t we're already using. And finally, the D is for derivative. And if you're in calculus, that's familiar, but if you're not, that's okay. That just means the slope on the graph. So if you try to imagine how steep or slanted that graph is, that's a measure of how quickly the error is going down. So if the error is going down slowly, then that's probably what you want. You don't want to have any jerky movements. But if it's going down really fast, you can use this component to kick in and try and slow things down so you don't actually overshoot the speed that you want. So this is simply the derivative. And to put it all together, and again, this is kind of a simplified form. I hope Abel forgives me. But it gets much more complex than that. But basically what you want to do is the output becomes a combination of these three things. So each of these can contribute to how much you want to push that gas pedal down, and they all have their own different elements to add to it. But if you use all three together and you choose the right multiples of each, you can actually get solutions that are pretty nice and smooth. So those letters I've written there, C1, C2, C3, those are actually what you get to tune, they call it. You get to choose those values and say, hey, I want to take, so much of the first component and a little bit of the second one and maybe just a very tiny bit of the third one, and try and get the right balance so that I get nice, smooth controls up to the goals we want. And remember, this has to do this as the terrain changes. So, 1 minute you're going uphill, then you're going downhill, and then all of a sudden there's a wind blowing at you. These have to adjust for it and try and keep your speed steady. So just as a real quick example, I'll show you a graph here, and we're going to imagine that this line I've drawn here is the goal. Let's say that's the 70 miles an hour, and you're going to start at 60 miles an hour. If you just used the proportional part, meaning you just looked at, hey, I'm 10 miles an hour away, let's punch the gas pedal, what can often happen is you get up to the 70 miles an hour pretty quickly, but then you go too far, and then it has to come back down, and then that goes a little bit too far, and then it comes back up, and if you aren't careful, it can actually oscillate back and forth and never really settle down. So the other goal, by using the integral part, is to watch for accumulating errors, and if you throw the derivative in too, you can have a couple better situations. For one, you can have it go up, I'm drawing this in green now, and even if it overshoots, it will dampen back down and level out. Not ideal, but it still is going to be a decent solution. Or if an ideal solution would be you nicely ramp up to the speed, right before you get to it, you slowly get out to it, so you have a nice smooth landing on your target value, and it keeps you nice and steady there. Now think about what Abel has to deal with, because he's dealing with, you talked about moving fuel around and talking about speeds and directions, but one of the most important things he has to worry about is getting a plane to land on an aircraft carrier. Well, think about the gravity he has to worry about. He can't overshoot that, right? If he overshoots, then the thing's going to smack into the aircraft carrier, and if he undershoots, it's not going to hit the surface at all. So he has to have that perfect, and it needs to be a nice, smooth landing on the target value. So you can actually find out tons more on this if you're interested. It gets into some pretty crazy mathematics, but that's the basic idea of it. And if I got any of that inaccurate, Abel's going to get me, I'm sure. But no, I think it's safe to say on my very brief overview there. All right, thanks again to the guys at Northrop Grumman. Everybody's really helpful and informative, and we really had an enjoyable time there talking to everybody.